Okay, so I posted the third assignment, and I think already there is a request to move it because we have an exam on Wednesday next week. So I'll move it to the weekend, Sunday. Is that what you wanted? Is that okay with everybody? Yeah. Okay, so it's a fairly straightforward thing to set up because we have seen it in class, but I wanted you to be precise because I was just throwing numbers of 1, 1, 1 for everything. But I want you to go after the transition from a one-dimensional flow to two-dimensional flow. And I also want you to look at what would happen if I have a finite wall at the top and the bottom instead of a symmetry boundary condition. Then what do you observe? Make comments on that. I won't tell you what you should find, but you will find the solution for that case. So in the last lecture, we spent quite a bit of time with COMSOL, looking at axisymmetric problems. What does it mean? How do we set it up? And we talked a lot about the physics in terms of transition from 1D flow to two-dimensional flow that are periodic in the axial direction, up and down. And that problem, there is a whole book devoted to it, I guess many books, and then thousands of articles. It's a very complicated dynamics that it unfolds as you keep increasing the rotational speed, going all the way to turbulent flow. Turbulent Taylor vortices have also been observed experimentally. And in terms of COMSOL, we learned again what is a swirl flow setting and what is a parametric sweep, convergence problems. We tackled with it for a while. You will tackle a lot in your current assignment. And then the creeping flow option that's available, which is kind of a approximation that gives you a good initial guess, and the symmetry boundary conditions, etc. So I want to continue with the modeling part of it now, going to concepts, discussing various types of symmetry conditions, etc. So for multi-phase flows, we're going to talk about the underlying concept on these development of these equations later on when we look at smoothing and averaging, etc. But this is the equation that is available in both COMSOL and Fluent, as well as in Star CCM and OpenFOAM, etc. So this is kind of inspired by how the Navier-Stokes equation looks, but it is not a rigorous definition. In fact, in deriving this from the Navier-Stokes equation, we find that we lose a lot of information. There is something called a smoothing process, and all those are hidden in this SIK, which is the source term, interaction between the two phases. So here we are thinking of fluidized bed reactor where there is a gas or a liquid fluidizing a solid. So the fluid and solid exchange mass, momentum, heat, etc. Those are all given in here. So the basic framework is that there is a transient or an accumulation term, and there is a convection term, and there is a diffusion term. The diffusion term is the del square. For example, del dot operated on another del. So the Laplacian on any field quantity, the field quantity phi can be velocity itself or temperature or species concentration, etc. And what they call gamma here is your diffusion coefficient or dispersion coefficient, and u here is the velocity field, and alpha or the volume fraction of each phase. Okay, so and rho L is the density of that particular fluid in that phase. So you have a template like this for each phase. You can have 3 phases, 4 phases, as many phases as you want. We conjecture that an equation like this will help us track the dynamics of these multi-phase mixtures, provided we can model this accurately. So we need to understand the sources of uncertainty in that S term, the source term, and we will do that once we look at the ideas behind what volume averaging is, where do we lose that information. But the template itself looks very much like the momentum equation that we developed, the Navier-Stokes equation that we developed, with transient and advection and diffusion term. So the advection diffusion phenomena are the ones that help in 2 things. I think I probably talked about it earlier. I don't remember, but let me see whether I can sketch that again. Do you remember, did I talk about this in this course? Mixing, dispersive mixing and distributed mixing concept. That's what these two terms manage. Okay, so when you want distributed mixing, that is, if you have a cluster of particles and you want to move them around to different locations, that's done by the large-scale velocity field. What kind of circulation that you set up. If you set up only a small-scale circulation, V can only take it around that region, and that is this term, the advection term, the first term. Okay, and the dispersion is breaking it up to homogeneous distribution in each neighborhood, and that is done by the second term that you see here. Okay, so it is advection, dispersion, or diffusion that drives towards homogeneity. But advection is very complicated. It can actually lead to instabilities, which we have already seen in the Taylor-Court problem. It is that term that represents the inertia, and the inertia destabilizes, viscosity stabilizes. These are two forces. One is a destabilizing force, the other one is a stabilizing force. And the same type of equation you have if you have, this is for so-called a mixture model. Okay, so in this model, you actually assume each phase has a template of equation like that, and the phases have their own velocity fields. Each phase can move with its own velocity, so there is a significant slip velocity, relative velocity between the phases, and that would be important when you have gas-solid, gas-liquid flows. But in some cases, you might have the phases behaving like one single phase. Can you imagine a situation where that might be a good approximation? Then we'll call that as a homogeneous phase, and we assign only one velocity value for the mixture phase. Okay? Typically, if there is no significant density difference, for example, between the particle and the fluid, then the gravity is not pulling on the particles with different force than on the fluid, so the particle and fluid move with the same velocity. Then you can have one velocity field that is shared by both phases. Then a simplified version of this model, the so-called mixture model, is available in Fluent and in all the similar software. But you then define what is a mixture density. A mixture density is just the weighted average, volume fraction weighted average of the density of each phase. And a mixture velocity is defined as a weighted average of the velocity of the individual phases. But we don't have information on individual velocity phases. We don't have independent equations to track that. So we track only the mixture velocity. Okay, so UM is the only unknown that we are solving for. And once again, in this framework, phi can be any quantity, including the mixture velocity or temperature of the mixture or composition of different species in a mixture. So when you have multi-phase mixtures, gas-liquid, for example, you need to also worry about interface mass transfer from one phase to the other phase. Examples would be you're producing steam in a boiler. So you're heating up water, it changes into phase into steam. So you have two vapor-liquid phases. And there is an equilibrium model that you need to worry about at the interface transfer. Okay? So the interface, there is mass transfer. If there are mixture of species on both sides, but if it is pure water being evaporated into pure steam, then water molecules don't have any resistance on the liquid phase, so there is no mass transfer resistance. But at the interface, there is a saturation temperature that determines how much of it will evaporate into the vapor phase. Okay, so these hopefully will become clear as we go and talk about in greater detail. I'm just kind of collecting all the models that are available in this collection of software, whether it is COMSOL or Fluent. There is a theory manual from COMSOL and a theory manual from ANSYS that I have uploaded to Moodle for this week. Okay, each one is about 800 pages long, and I don't expect you to study that. I don't expect you to become an expert in that. With time, as you need, you will learn, open it up and learn what these various models are, but it will be useful for doing your project. Okay, because the project, you need to know what sort of model equation should I assemble to study the physics that I'm interested in. So for that purpose, I put that, so that's the project lists are coming out tomorrow or day after. Okay, and so the concept of periodic boundary condition we already talked about. Okay, but this is again described in as an example in the ANSYS theory manual. And what precise mathematical equations are imposed when you have a periodic condition. Okay, so here is an example of a string of cylinders or spheres in a channel. Okay, so you have flow coming in, and it encounters the first cylinder. Let's fix it as cylinder, so it's 2D. The next cylinder and the next cylinder. Okay, so when I arrange them at equal distances, the one option is for you to go ahead and solve without making any simplification. This is the geometry. I have 3 cylinders, one behind the other, and I have an inlet boundary condition. You can build the geometry very easily in COMSOL and solve for that. Okay. A more clever way would be to say, I have a repeating pattern, so why can't I take a subunit of that? Because I can just translate that. For example, if I take this block, I can translate that by 1 unit to the center here, and I have the same block. So if I know the velocity here, I know the velocity there. Why do I have to solve for the entire length? Why would that argument make sense? Because if you solve it over the entire 3 cylinders, you need much more grid points. You are going to solve a problem that is 3 times as large as compared to 1 unit cell, if you can extract that unit cell. Okay? And when you do that, you need to worry about how do I specify the conditions, the boundary conditions. So here I specified it as an inlet condition. So I can put any velocity profile, and then the flow will evolve from that. Okay? But when I'm isolating a particular unit as a periodic unit, I need to make sure that what I specify here is the same as what I specify there. Okay? So you can identify these 2 planes and say they are periodic. Periodic is different from symmetric. In what way is it different? Symmetric simply means that what happens on this side is the same as what happens on that side. So it is a reflective condition. Periodicity is what happens in one part of the plane is the same as what happens in another part of the plane. Okay? So for that, the geometry itself should have the same features on both sides. Okay? Any questions on that concept of periodicity? Because I'm going to ask you more questions if you don't.
So that figure is symmetrical as well, right? But in the center.
Yes. You can say that it is symmetrical under low Reynolds number conditions. So we are going to talk a little bit more about this problem, because a problem like this can have very complicated consequences. So it allows us to think, to understand how to set up these problems. Okay? So yeah, that's a good question. Let's come back to that.
How valid is the assumption that U is equal to U is equal to UC? At all the inlet conditions are the same. How valid is this assumption?
How valid is this assumption? UA is equal to UB is equal to UC.
For an infinitely long U, it's definitely valid. I mean, it depends on the inlet velocity as well. As you said, for turbulent conditions, it may not be
Right.
valid.
So, I was going to ask all these questions as discussions, but you are raising the question and providing the answer too, right? That's a good question. How valid is that assumption? Under what conditions is that valid? If I impose periodicity, I am imposing that, so it is going to obey that. Okay? But the question then is, I can impose any nonsensical condition and get a solution. Ultimately, I want to compare that against some real situation. So the real question is, how realistic is that when I compare to an experiment that I do? Okay? And the answer is, over certain conditions, it may be valid, not under all conditions. And what are those conditions? That depends on the physics that we are solving. Here we are talking only about geometry, similarities in the geometry to see where the periodicity is. But over these domain, we are solving flow equations. So assuming that these statements are valid, that is velocity at A is equal to B equal to C, similarly for pressure, this is the equations that it imposes. When you identify them as periodic, it just says, I don't know what the value of the velocity is in this plane. I'm going to let them as unknown symbol, U at that point, but I'm going to make that the same as the U at the other point. So when I'm constructing my matrix, I'm going to treat these additional conditions, and these are the additional conditions that you see in 120. U on the left plane at a point is the same. After I discretize it, I will have a set of grid points. So the velocity at this point is the same as the velocity at that point. I don't know what they are. They're going to be solved as part of the solution. Okay. Now, getting back to this, how realistic it is, it depends on what sort of boundary condition I input. For example, if I input a flat profile here, and then say that, ask the question, is this going to be the same as this? I solve over the entire 3 cylinders. And then ask the question after I've solved it, is this the same as this? What do you think the answer would be?
I don't think so, because
The inlet will have a certain impact on the flow as it evolves. So this concept of a developing length becomes important here. It needs a certain length for the flow to become fully developed, and then it can repeat itself. So if you don't have any obstruction, it takes a certain length, it develops into a fully developed state, and the velocity profile doesn't change. But if you have obstructions after it has developed to that length, it will obey the obstructions. So it will be periodic after that. Okay? So it depends on the Reynolds number. It depends on how strong the velocity is. So if the velocity is very high, it may take 10 cylinders before it reaches the fully developed state. And then you will have a periodic state. Okay? So, so in that sense, periodic state is an assumption, and you need to be careful how you impose it and how you interpret the results coming from that. Yeah.
Can we give a precise definition for Reynolds number?
There is no unique, precise definition that you can apply universally. But what you can say is you need to choose a length scale, a velocity scale, and a fluid property. So the Reynolds number is defined as dV over nu. Nu is the property, okay? But you need to choose what d is. In this case, you have 2 choices. You can base on the diameter of the cylinder, or you can base it on the height of the channel. There are 2 Reynolds numbers that you can define. So if you look at the entrance length information, we say, for example, for the flow to develop along the length of a channel, I need 10 widths. Then you would use the width as your scale to calculate the Reynolds number. But if you're interested in, there is a wake that forms behind these cylinders. If you want to understand the wake dynamics, then you would use d as the diameter, as the characteristic length for your Reynolds number. Reynolds number based on that particular size. Okay, so Reynolds number as a concept is essentially a ratio of inertial to viscous forces, but how dominant is the viscous force is determined entirely by the property. How dominant is the inertial force is determined by the velocity magnitude and some sort of a length scale. Okay. Any other questions? Okay. So we talked about difference between symmetry and periodicity. So one question to ask, I think that you raised, is in this case, are they the same? Right? The answer to that is, if the Reynolds number is very, very, very low, close to the creeping flow, it might be same, but it need not always be the same. Okay? Because what can happen is you can have a flow that is going like this. Okay? And here also it does the same thing. So it is still periodic, but it is not symmetric. I think it's too clouded, so let me just take. So if, for example, the flow is not symmetric about this axis, but it crosses like this, okay, and then it crosses like that, okay, then I don't have symmetry, but I have periodicity, because the velocity vector is having the same direction in both places. Okay, and when can that happen? If I have, for example, a rotation. These cylinders are not just fixed, but they are rotating. Okay, I can create a flow there will be something like this. Okay, and I can still have a periodic condition, but not a symmetric condition. But if I don't have that, if they are all stationary and low Reynolds number, then I will have both periodicity and symmetry. But if I have no rotation but a very high Reynolds number, then I will have a wake, something like this. Okay, and then again I have gradient there. So I don't have symmetry, but I have periodicity. Okay, so it's a very powerful condition for abstracting a simple unit cell from a more complicated repeating units. So for packed beds, these kinds of models are used. For example, I don't know whether you have seen it in the transport course, so-called cell model. Okay, so you take a single particle and build a cell around that, and then you treat your packed bed as a collection of these cells organized in some way, and you can, yeah.
So one more question, similar, like for turbulent flow, okay, if the inlet conditions are periodic, but there might be eddy currents that are different in all the cases, right? Can we still model them correctly?
That's a very good question. People actually that attempt to do so-called DNS, direct numerical simulation of turbulence, and that essentially means I'm going to solve the Navier-Stokes equation, which we solved in the last class, but at very high Reynolds number, right? And they do that by taking a box that is periodic in all three dimensions, meaning what happens in the top is the same as what happens in the bottom, what happens in the front is the same as what happens in the back, etc. And they use very sophisticated methods of solving the Navier-Stokes equation, not COMSOL type finite element method, but so-called spectral methods, where they take Fourier series, expand the solution in terms of Fourier terms. And so what happens is you can impose periodicity, and people have done that, and then try to extract the statistical behavior of the flow to characterize turbulence. Okay? But you cannot extract structures that are larger than the cube because you don't have them. And it can produce structures that are smaller because of the mechanism is there to transfer energy over all scales. So from the large scale to smaller and smaller scale. So you will, in fact, that was the attempt to see whether you can predict the Kolmogorov distribution, energy distribution from direct numerical simulation. And that you can do. Okay, but the starting length scale would be determined by the size of the box that you pick in subsets, perhaps. Okay, but yeah, you can use. People have used periodic boxes for studying turbulent flows and for studying porous media flows. Swirl flows is another feature that is available, and we talked about it a lot in the last class. So essentially, you have axisymmetry means that the plane that you see that is shaded here, the flow pattern that you observe on the plane will be the same if you take any plane as you rotate around this. Okay? But swirl flow essentially means that you also have a component of the velocity that is cutting through the plane, but still it remains the same everywhere. On any point that you take here will be the same on a corresponding point on any other plane. So 3D axisymmetric flows are governed by, 2D axisymmetric flows with swirl flow are governed by all the three momentum equations. You have all three velocity components. And so this is the difference between 2D and 3D axisymmetric flows. The velocity component depends only on two spatial dimensions in both cases, but in the, with the swirl flow you have this velocity. Without swirl flow you don't have that. And in the 3D flow you will have a velocity field that depends on all three velocities of three components. Now, that is a misnomer. I shouldn't have called it axisymmetry. What happens in some cases is the axisymmetry that is continuous, meaning the profile that you see at any plane should be the same. That's a continuous symmetry. Okay? That is broken, and you will see some sort of a wavy vortices that are going around. So we say that the continuous symmetry is broken into a discrete symmetry in the angular direction. That is exactly what happens in the Taylor-Couette flow in the axial direction. Okay? If this is a channel, the one-dimensional flow is the same no matter where you take, where you sample. It just decreases, right? The profile is like that. But once that becomes unstable, you have flows that have these cells. So what was continuously translatable now becomes discretely translatable, meaning if you move this by one wavelength, you get the same pattern. That you call discrete symmetry. So the the symmetry along the z direction is broken into discrete one. But it is still continuous in the angular direction. That symmetry is also broken once you exceed a certain rotational speed, and then you get these waves. And these waves will have a finite number of modes as you go around, and they will close on themselves in 2π. Okay? And these can be moving in time, then you get a traveling wave solution. And that's what makes this Taylor-Couette problem very, very rich in dynamics in terms of possible solution patterns. Okay, any questions on that? Idea of an axisymmetry with swirl flow and breaking of these symmetries. And the breaking of symmetries occurs through instabilities. I will show you a few more examples in nature where that happens all the time. Okay? Now, the next concept that we should be prepared to deal with as we are learning to equip ourselves for solving a variety of complicated engineering problems using these tools is moving reference frame. What does it mean? How is it formulated in theory, and how is it implemented in COMSOL and ANSYS and any other package? So here is a problem. Maybe let me just suppose I have a cylinder, a cylindrical vessel, and I put some sort of a paddle, a stirrer, okay, and this is rotating with a certain angular velocity. Very commonly used configuration in chemical reactor design. Okay, what you want to do is mix the two reactants that are fed into it, maybe from a pipe, so that they can molecules can come together and react. And what we want to do is achieve a very homogeneous flow condition. That's why we have these impellers. How do I solve this problem with what I've known so far from COMSOL? I can build the geometries, right? But what would I specify for the boundary condition for the rotating impeller? I know its angular velocity, right? But I need to build a mesh, and this impeller is going to be moving through the mesh, right? So do I remesh every time after I move the impeller? That's an enormously complicated problem, the way that it is presented to us. But there is a very simple solution to that. The solution is I keep the impeller stationary, but I rotate my cylinder, right? So if, for example, I sit on the impeller and I observe what happens, the next impeller is going to be at the same location with respect to where I am. So it is going to look as if it is stationary. But what would the wall look like? It will look like it's moving in the opposite direction. If I'm rotating this way, it will look like it's rotating in the opposite direction, right? So then I don't have to remesh or anything, right? The geometry gets simpler. I still have a wall. These are modeled as walls. I insert them, but they are fixed, and I mesh around that wall. But I have another wall, a cylindrical wall, but that cylindrical wall has now a velocity because it's a sliding wall, and I already know how to do that. We saw it in the last class, right? So that's the idea or motivation for putting a moving reference frame, switching the reference frame from which we want to solve the equations. Okay, is that clear? Yeah.
So in reality, when the impeller is moving, we have a pretty high swirl flow close to the impeller as we move more towards the wall. We have most of the conditions. Whereas when we are modeling, it is the other way around.
Right. That is in the moving reference frame.
Yeah, how is that? I mean, like, does that affect? I mean, is it the same?
It is the same if you translate back to the laboratory coordinates. Okay, because if you're sitting in the impeller, you're seeing the wall of the tank moving very fast. So to you, it'll look like the fluid there is moving very fast. But the fluid there is actually stagnant because the wall is stagnant, right? So it is essentially a translation of the velocity reference frame. And that's what I'm going to show you next. how that is done. Okay, so translating the reference frame in which we wrote the Navier-Stokes equation in a fixed laboratory reference frame. We can move that to any other reference frame that we want. And if you are able to do that, then we can solve the problem in that moving reference frame if it becomes simpler in that moving reference frame, but reconstruct by transforming back into our laboratory frame. So we go from laboratory frame to a moving frame, solve the problem in moving frame, come back to the laboratory frame for interpretation.
So
Yeah?
you just have to change the coordinate systems.
You just need to change the coordinate systems. Yeah, exactly. Right. So a coordinate reference is essentially a kind of a structure that holds the building, right? And you can construct it in any way you want. Whether you write the Navier-Stokes equation in Cartesian frame, cylindrical frame, spherical frame, and there are a number of other coordinate systems. It's still the same dynamics that is governed. So the reference frame shouldn't matter. So we can move to a reference frame that is convenient. Why do we use cylindrical coordinates? Because it fits a cylindrical geometry very well, right? But we can solve in a cylindrical tank using Cartesian frame without invoking cylindrical coordinates, right? So the same thing with spherical coordinates, same thing with spheroidal coordinates. There are a number of other orthogonal coordinates as well, right? So if you recognize that you can do this transformation of coordinates, then the problem can be made to look simple in another reference frame, including a moving reference frame. Not only, like if you go from Cartesian to cylindrical, the motivation is because my object is cylindrical in shape. But if my object is moving, I go to a moving reference frame. Okay? And, okay, that's easy in this particular case. What happens if I have the picture that you see on the left? So I have now baffles. These are baffles. And in industry, these are used. Why? Because you want to promote mixing, and baffles tend to promote mixing. Otherwise, it can encounter into kind of a solid body, rigid body rotation. You want to break those. So now this impeller that you see here is rotating at an angular velocity. Even if I sit on top of the impeller, what will I see? I will see these baffles moving around, right? And so I need to remesh because the reference frame doesn't give me the advantage anymore. Okay? So what does Fluent do? What does COMSOL do? They have something called multiple moving reference frame. Okay? So you divide the zone into two zones shown by the shaded line and the dotted line. Okay? So inside that you put it into a moving reference frame. Outside that you solve the equations in a stationary reference frame. Then what do you have? You have a problem only at the interface because you have two velocities at the interface. As you approach the interface from the inside, the velocity is with respect to a moving reference frame. As you approach from the outside, it is with respect to a fixed reference frame. But you know physically that the velocity should be same, unique, right? So you impose the condition by smoothing things at the interface. So it introduces some sort of an interpolation error at the interface. Okay, that you can control by controlling the grid size and the time step. If your time step is large, then the moving reference frame can move a lot of distance in one delta t. And then matching the velocities would be more difficult to do that. So typically multiple moving reference frame ideas will require you to use smaller time step size, meaning the computational effort will be larger. So mathematically, this is what you need. Okay, Vr is the relative velocity that you see here, and V is the absolute velocity with respect to a fixed reference frame, and UR is the reference frame velocity itself. That is, my reference frame is moving with a certain velocity in a certain arbitrary direction. It could be changing with time as well. That is, a reference frame accelerates. Okay, and that reference frame velocity UR, since it consists of arbitrary motion, can be decomposed into two parts. That is, any arbitrary motion can be always specified as one due to translation, the other one due to rotation. Okay, and so that's what is given here. UR, the moving reference frame velocity, is given as sum of the translational component of the reference frame The reference frame itself is translating, and the reference frame itself is rotating at a certain angular velocity. Okay, so if you open up Fluent or COMSOL and check this box, it'll ask you for these two pieces of information. Okay, what is your translational velocity? What is your rotational velocity of the reference frame? And then it solves the equations using that coordinate transformation. Okay, in this particular case, what do we have in the stir tank that you see in the red? What is Vt and what is omega? Vt is 0 because it's not translating anywhere, right? The reference frame is fixed in one place, but it is rotating. So the omega is in general a vector, because you can have rotation about x-axis, about y-axis, and about z-axis. In this case, it has only one component, rotation about the vertical axis. Other two components are 0. Okay? So it's a fairly easy thing to input and set up once you understand what it means and what are the implications of it. But what happens to the equations of motion when you subject this to a moving reference frame? Okay, here is another example of how you might find it useful. So this is the figure on the right hand side is a centrifugal pump or a turbine. Okay, so this turbine that is in the red is rotating, and there are thousands of vanes, hundreds of vanes, whatever, right? So what you want to do is, these are moving, so it's very difficult to set up a moving boundary inside a domain. Of course, newer algorithms are coming into place, like the immerse boundary that Cheng Guang was talking about today, right? Those will allow you to handle a moving boundary, and we will see when you do the computational algorithms, what is the idea behind immerse boundary method to handle this in a more elegant way than what is currently handled in these simulators. But what they do here is illustrate through a simple, take two vanes that are next to each other that you see here, okay? And that has an inlet and an outlet, and if you put that in the moving reference frame with an angular velocity about this point that is specified, then it looks like that's a stationary problem. And why can I take only those two vanes of these 100 vanes or so? Because it's periodic. What happens here is the same as what happens there, same as what happens there. So I can impose periodic boundary condition here. I can put this domain in a moving reference frame, right? And then I have an inlet and an outlet. So I'll be able to predict what is the net discharge and what is the increase in pressure, whatever it is that I'm interested in computing over that. And then just add them up for as many number of unit cells that you have. Yeah.
Just to make sure, if we apply periodic boundary condition and some boundary condition, for example, let's say pressure and velocity, can we apply the periodic on just velocity and you can calculate the pressure from this boundary to that boundary or not?
That's a good question, very good question. Actually, I should have addressed this before. Let me go back to that and address that now. Did you understand the question? When I have a periodic condition, I think that problem, the impeller problem probably triggered that question in your mind, right? Can I impose just velocity as being periodic in these two planes, or should I also specify pressure to be periodic? That's what you're asking, right? Or will it compute the pressure, right? What do you think? Anybody, what do you think? What is
think that COMSOL can calculate just the both of them. But
I think they're coupled because
They're
the
coupled.
source of velocity and pressure gradient.
Velocities and pressures are coupled through the continuity and momentum equation, right? So if the velocity is periodic, the pressure is expected to be periodic too. But there is a but there. That's a finer question. That is, if the pressures are the same at these 2 points, what is driving the flow? Which force is driving the flow? It is the pressure gradient that must drive the flow, right? If I have a periodic array and it's a channel, I need to have a pump here to push the fluid through, right? And so that means I'm spending some energy overcoming friction at all these solid surfaces through viscous dissipation, right? So that sense, the pressure here cannot be the same as the pressure there, right? Because there is a pressure gradient, right? How do you resolve that problem? The pressures are periodic and not periodic. So what really happens is, if you plot the pressure variation along this length, the pressure variation would be something like this. So on the average, the pressure would decrease because you are expending energy. There will be an average pressure gradient between these 2 points. Okay, but there would be a pressure buildup as it expands. Like here, the fluid accelerates, so the pressure energy is converted into kinetic energy. Right? So, and as it recovers, the velocity decreases. That means the pressure must increase. So the pressure here in this part may actually go up, and then it starts going down again, and then go up. But this peak will be below this peak, will be below the next peak, etc. Mathematically, what it means is the following. The pressure, which is a function of x, y, and z, is, and if this is the z direction, is decomposed as one that is a function of z, and another that is a function of x, y, and z. Okay? I can always write a function as a sum of 2 functions. I don't lose any generality in doing that, right? But when I do that, what I'm saying is, if I take the gradient of that, then gradient of this, I guess I should use 3 different symbols. Gradient of P is gradient of P bar plus gradient of P tilde. Now this gradient of P bar, this is only a function of Z, right? So that is going to give me only dP dZ. Okay, so that is going to be treated as an input. That is the pressure gradient that drives the flow. Remember, in COMSOL, I can either specify the velocity here, or I can specify P1 and P2. If I have a P1 and P2, I set up a pressure gradient, so that will drive the flow. But if I specify P1 and P2, I cannot specify the velocity. You have to compute the velocity for me. But if I specify the velocity here, I cannot specify the pressure here. But I can specify the pressure there, right? And then it will calculate what the pressure is. I can back calculate what the pressure gradient is. So there is a unique relationship between the flow rate and the delta P in channel flow, right? But you cannot specify both delta P and Q on the flow rate. But when you do encounter problems like this, what you do is you go into the Navier-Stokes equation and look at this term gradient of P and split it into 2 parts, and this part is periodic, but this part is a given number. You input that number as a source term. That's the one that drives the flow. When you have that, remember, if I say this is periodic, I cannot specify what the velocity field is. All I can do is this velocity is the same as that velocity. So I don't specify velocity anymore. But I specify this gradient of P across this. What is the pressure that is irreversibly lost in pumping the fluid through that? Right? You follow that? Any questions on that? Is it clear? There are some puzzle phases.
It is clear, but I have a question. When we have those peaks decreasing along the z-axis,
Yeah.
how can we say they are periodic?
The final understanding comes when you realize mathematically we have said that we can split this, right? So physically what we need to do is take this profile and put a straight line through that and subtract that, the straight line through that. Then what you will find is that the pressure becomes something like this. So if you take a function like this and a function like that and add them up, what do you get? Geometrically, if you take this function and add that function, you get this function, decreasing this. Okay? So this is what the reality is, and we are saying we are going to treat it as sum of these two. And one is the unknown that I'm going to specify as periodicity. So it is this P tilde is the same on these 2 planes. but there is a P bar that corresponds to this gradient that I specify as an input into my simulation. That drives the flow.
So follow-up question. So
Yeah.
we can never produce that graph, right? Because we don't know how long they are. Because if you are assuming it's periodic, we don't know how long the actual tube is, or in this case, how many cells we have. So this graph of reducing P, we
Yeah.
don't know where it will level off unless we don't know the entire length and calculate it separately. It won't be given from the simulation itself or the calculation.
No, from the simulation you will get that.
Because we don't know the number of cells that are periodically repeated, right?
That can be 100,000.
We can specify a number.
You don't. What you are going to do is solve only over one.
That I understand.
Yeah.
So you said that the pressure is reducing constantly. So there has to be a starting point and end point, because in reality it's a finite system.
Yeah. Yeah.
And we are assuming that this finite system is infinite by taking a periodic system. So we cannot calculate this actual initial and final spot
Right,
through
right.
this calculation.
That's a very valid point. So periodicity in that sense is an idealization. So you will never be able to use it to construct real systems. But depending on the length to diameter ratio, if you have long channel like that and you find the periodicities of this order, the solution that you get by taking one cell will give you a reasonably good approximation of what the delta P is over the entire one by adding it up, except the errors introduced by the entrance length effect here and the exit length. And exit length is smaller normally because the flow is this way, so the effect of this exit is felt only maybe 1 or 2 grid cells behind. Whereas this one, for large velocities, can propagate a long distance. So that's a very valid point. So if you're taking this idealized periodic solution result and applying it to a real system, you need to account for the entrance effect. Yeah. Very good. Interesting discussions. Any other question?
So we just need to model one of this part and then scale up.
And then scale it up. Yeah. Right. Yeah. Okay. So any questions on this one? The idea of what a moving reference frame is. Mathematically, conceptually, we talked about what it is. Mathematically, it is the relative velocity is the absolute velocity minus the reference frame velocity. A reference frame in which I have my object. Okay? And that reference frame velocity can be given as this expression without any loss of generality, because it's just treated as a combination of translation and rotation motion. An arbitrary motion is given as a combination of these two. In a sense, by specifying these three, you can construct any arbitrary reference frame motion with that. So COMSOL and Fluent will require you to provide those information, the VT, the omega, etc. And this example simply shows how we scale, how we extract one unit to study the detailed simulation and then get information on pressure increase and flow rate through one pair of wings, and then you can integrate that to get the performance of the entire pump or the compressor or whatever that is. So the mathematical part of it is what is given in this one. Okay, this is coming straight from the ANSYS manual. So the green line that you see here is the stationary laboratory reference frame, okay, X, Y, Z. And then you have another reference frame located around X, Y, and Z. That center of the reference frame is undergoing motion, arbitrary motion, with the translation velocity and the rotation velocity. And our CFD domain is in that reference frame. So we need to formulate the equations in that reference frame from the fixed reference frame that we have by simply applying the rules that we have agreed upon. Okay, and when you and what does that rule simply means? If you go to the previous one, wherever we have V, we write it as VR plus UR. Just take it to the other side. V is equal to VR plus UR. Okay, and UR is known. VR is what appears in the original Navier-Stokes equation, and I want to get rid of it and get it in terms of VR. VR is the reference velocity in the moving reference frame. So that is the velocity that I would see if I sit on that impeller and move with the impeller speed. Okay, so the continuity equation doesn't change at all when you do that, because when you're taking all the spatial derivatives, that VR UR, the reference velocity, can change only with time. Okay, so it's essentially the origin of that velocity that moves arbitrarily, either translates or rotates. So there are no spatial derivatives in that. So all the spatial derivatives drop out, and you get, instead of V, you get VR. Continuity equation remains the same in a fixed reference frame or in a moving reference frame. The velocity here is measured in a fixed moving reference frame. The problem comes when you take the Navier-Stokes equation, and you will recognize many terms in the Navier-Stokes equation: the gradient of P, the stress, the external body force, and the left-hand side. Okay, so this is our original advection term in the Navier-Stokes equation. That was in terms of rho VV, VV being the dyadic product. Now we are replacing it with VR plus UR. Okay? And when you do that, you get these additional terms. All these terms will be zero if you put the moving reference frame angular velocity to zero, which is omega to zero, or the translational velocity to zero. So here A is the acceleration term. This is the translational velocity. So if it is moving at a constant velocity, then there is no acceleration. This term will drop off. Okay? If it is moving at a constant angular velocity, there is no angular acceleration, then this term alpha will drop off. Can you see in the back those two terms? So this is the equation in a moving reference frame that is solved by all these packages. Right? None of the terms on the right hand side change. On the left hand side, it gives birth to a lot of new terms. These are all the pseudo forces because you are in an accelerating reference frame. Okay, so these are all in terms of the moving reference frame velocity, and this is the acceleration, and this is the angular acceleration. Do you recognize what this term is? Omega cross R. A centrifugal acceleration, omega squared R, right? And this is omega times dr. This is called a Coriolis force. These are forces that are arising out of the fact that we are in a reference frame that is moving. Okay, and these forces are important in geophysical fluid dynamics. The jet stream, the Gulf Stream in oceans, they are all governed by these terms. Okay, and here this is the Earth's rotation, for example. Right? So these terms arise and are important in certain flow configurations. Okay, so it's exactly the same equation other than this. So these are treated now as a source term. This extra term moved to the right hand side from a computational point of view. Take all these as source terms and move to the right hand side. You have the same framework. A diffusion term, a convection term in a moving reference frame. The same machinery of discretization and solving will work in a moving reference frame. Okay, so that's the idea behind the moving reference frame, to make the problem simpler. So to do any choice of a coordinate is to make the problem appear simple in that coordinate frame. And this one works in when you have rotating machinery typically. Any questions on that? So this one we already talked about it. So when you have multiple reference frames, that is a stationary zone, which is this part, and a moving zone, a rotating zone, which is this part. Okay, so there is an interface. You are dividing your domain into two parts. One part is stationary, the other part is rotating. And the reason for that, of course, doing that is to handle baffles with a stirrer. Okay, so that in each domain, it looks, the geometry doesn't distort as the rotation takes place. But the problem we have is at the interface. Okay, because at the interface, as you approach this, one velocity is based on fixed reference frame, the other velocity is based on moving reference frame. So you need to smooth them together so that that impact doesn't destroy the solution accuracy overall. You need to smoothly patch them. Okay, so we have talked about number of different isolated ideas that are implemented in these simulators to learn how to formulate these kinds of problems. Now I want to come back into the stability issue. We talked about the stability issue for the Taylor-Couette problem, but this is the one that's going to help us understand why does the Navier-Stokes equation have such complex behavior as you increase the forcing, leading to turbulent flow, and then maybe leading to multi-phase flow when it interacts with a second phase. So these are concepts of stability. We will see the mathematical implementation of what stability is, which we haven't done so far. And then later on in the algorithmic part, we will see what algorithms are available to determine the stability. So here on the top left, I have 4 images. Okay, so you have a parabolic dish and you have a particle in here. If I kick this particle by applying a force on either side, what happens to the particle? Just comes back to its position, dissipates the energy through friction, and comes back to its equilibrium position. And that's what we will call a stable equilibrium. Okay? But if I have a situation like this, where I have an inverted parabola and I'm keeping the particle at the top, it can be stabilized. How is it? It can be an equilibrium position. Why can it be an equilibrium position? All you need is forces to be balanced. So the weight is balanced against the upward force. But it is unstable in the sense the slightest perturbation that I give it takes it away from that equilibrium position. So the concept of equilibrium is a position that doesn't change with time. Okay? And the concept of its stability is if I perturb the system, does it go back to that state or does it go away from that state to a different state? Okay? And if you take this one, you have a so-called neutrally stable system because you give it a kick, it'll just go and stay there. Okay? So every position is an equilibrium position. And in this case, this is non-linearly unstable. What does that mean? The minima that you have is small. So if you give it a small perturbation, it comes back. But if you give it a large perturbation, it will go away. So this is the idea of a linear stability, meaning small perturbations, if it becomes stable, you call it as a linearly stable system. But you still don't know what happens to the nonlinear response if you give it a large perturbation. And turbulence is about that, large perturbations in the flow. How do they grow? How do they feed on each other? And linear stability is about onset of transition from one state to another state. That is from a one-dimensional Taylor-Couette flow to a two-dimensional Taylor-Couette flow to a three-dimensional Taylor-Couette flow. Right? So those occur through small perturbations in the experiment that can trigger it to flip. Any questions on that concept? You have all seen that before? Okay. So here is an experiment that was proposed by Benjamin, one of a very well-known, famous fluid dynamicists. So the experiment is the following. You have a wooden block, okay, something like this. And into the wooden block, you drill a hole and you put a wire, steel wire, through that you see here. And you can adjust the length of the steel wire from here to there by pulling and pushing through this. Thought experiment you need to do in your mind. Okay? And then you are seeing it from the side. From this side, when you see it, it looks like this. Okay? So what would happen to this wire as you increase its length? For very, very short lengths, it's going to be stiff. It's a steel wire, it's going to be stiff, and so it will be vertical. But as you keep pushing it in so that the length increases, it develops some flexibility, right? So it can go either one side or other side. And this happens in nature in a number of different situations. So it's called a symmetry breaking bifurcation. That is, a solution branches into two parts. One goes to the right side, the other one goes to the left side. Now, if you ask the question, why doesn't the vertical one remain like that as I increase the length? Answer is the weights are balanced, so it is an equilibrium position, but the gentle air that blows on it will cause it to go one way or the other way. That means it is an unstable equilibrium, just like the one that we saw here. Okay, and this diagram is illustrated typically in the following form. So I plot the length, and on the y-axis I plot the angle, theta. Theta is this angle of deflection. Okay, so the angle of deflection from the vertical is theta, and the length is from here to there. So I control the length, and I observe the deflection. I'm going to plot one against the other. And what I find is, at very short lengths, the deflection angle is 0. But once I exceed a critical value, I get either a positive angle or a negative angle, like this. So the solution branches like this. But there is a solution that is also an equilibrium solution, but it is unstable. Okay? So there is a stability change at this critical point. So this point is called a pitchfork bifurcation point. There are computational algorithms that will allow us to precisely locate where that is. Okay? That is, the control parameter length, you want to know at what length this vertical position becomes unstable with respect to this other one. Okay? And you can determine the stability of this, and you can also have variations on the theme, which is in some cases you have a stable solution and the solution folds back on itself. Then there is another stable solution there. So if you continuously increase the length, it will snap and go to that. But when you decrease the length, it doesn't snap back at the same position, it snaps back at a different position. So there is some sort of a hysteresis behavior here with respect to the length. So this would be called a subcritical pitchfork bifurcation. That would be called a supercritical pitchfork bifurcation. Because you increase the length and decrease the length, it follows the same path. Like that. Okay? Any questions on that? You might ask, what does this all have to do with fluid mechanics, computational transport phenomena? I think I talked to you about one problem, and I'm going to make this as one of the projects, is the sudden expansion problem. That problem exhibits exactly this behavior. We actually did some work and published a paper in the 90s, I think. So the flow will become like this. The jet comes and expands. There is a circulation there. It's very easy to set up in COMSOL. Okay? But what you will find is, as you increase the flow rate, the symmetry is broken. And then you have a jet that would go something like this. So one of the vortex becomes small, the other one becomes large. The jet preferentially goes over one side, and it is steady state. But if you take the mirror image of that, that will also be a solution. So you can trigger the solution to go into the other state as well. So fluid mechanics exhibits such complex behavior in many, many, many different situations. Flow past cylinders, flow past spheres, flow in sudden expanding channels, and Taylor-Cohen flow, etc. So we need to understand the dynamics of this in order to be able to interpret the results that come from simulations like COMSOL. Okay, any questions on that? So what are the important points in this slide? That there are equilibrium positions that are stable and unstable. They can coexist, and unstable ones, if you make the slightest perturbation, will go away from that. So it's very difficult to realize them in an experiment, because in reality there is always disturbances. So yeah.
What causes the distribution
In the expanding channel? Good question. What causes the disturbance to move the jet from being symmetric to non-symmetric? Any slightest, in an experiment, any slightest imperfections in the corner. Okay? If one corner is slightly blunt compared to the other one, that's enough to cause the flow to go to one side.
In a higher velocity.
At higher velocity. So you need to exceed a certain critical Reynolds number, and that Reynolds number turns out to be about 130, I think, for that particular problem, based on this width and the inlet velocity. Okay. In a numerical way, you can ask the question, why does it flip from one to the other? The round-off errors in numerical calculations can do that to produce enough disturbance. So it is linearly unstable, so the disturbances grow. Depending on how well you have machined these, you can delay the transition. Okay, but once you exceed that, soon enough, you will have this transition going away. If the machining is so perfect, you can delay that for a while. But the inherent instability is in the equations. So all it needs is the growth of the minor imperfections.
So we can see some critical value in experiments
Yes.
and some difference in simulation, and like two different critical values in two different simulations.
No. Because the critical phenomena is embedded in the dynamics of the equation, it will always occur at that point. Okay, but there is, when you're doing an experiment, you need to worry about how long do you have for the disturbance to grow. So you can look like it is delayed, but when you find the final equilibrium amplitude and then extrapolate back, for example, one way of doing the experiment would be, in fact, this is what we did in our paper, measure the length of that wave. When it is symmetric, the length of the wave on the top and the bottom should be the same. Right? But when it is non-symmetric, there will be a difference in there. So the difference will go to 0. So we plot the difference against the Reynolds number at various values of Reynolds number. And then you extrapolate it back. That is, you get a few points here, and then extrapolate it back. You will, in an experiment, and you'll get the same value that is predicted by theory. Because that instability at that critical Reynolds number is embedded in the dynamics of the equation. So it's not, you cannot manipulate it. Yeah, it's a good observation. Any other questions? Now we are going to get into a little bit more mathematics of analyzing these dynamical systems, which I think is very important. Anybody who is doing modeling needs to understand these concepts of stability, how is stability analysis done, how are equilibrium conditions determined. And we started off this course with this equation, dy dt equals f of y p. We learned how to solve this f of y p equal to 0. That is the steady state solution. That is the equilibrium solution when there is no variation with time. And when there is variation with time, you have an initial condition. We learned how to solve that with ODE 4.5, and you have done both. So you know which tools to use to analyze solutions, but we want to now conceptually analyze and understand this concept of a linear stability and linearization in particular. Okay? So what is linearization? Linearization is embedded in this idea that you see here. The trajectory to that equation, the trajectory of solution to this equation, can be decomposed into a steady state part and a perturbation part. Okay? And geometrically what we are saying is, if I plot y as a function of t, and if the dynamics does something like this, I can draw the steady state line, and if I blow this up, for example, there is my steady state, and this is the real solution. This would be my perturbation, y prime. Oops. As a function of time. Ys is the steady state, right? So I'm decomposing the entire solution into a steady state part and a perturbation. In linear analysis, I need to keep these perturbations very small. Why is that? That you see in the second equation. Okay? But what is the second equation? It is the same equation as this after I have substituted for y of t from this decomposition and do a Taylor series expansion. So you're all familiar with Taylor series expansion, right? So what would this look like, for example, this f of ys plus y prime, the parameter remains as the same. What is the Taylor series expansion of this function around ys plus y prime? Okay, that is y has been replaced by ys plus y prime. Okay, that's going to be equal to the same function at ysp plus df dy at ys multiplied by y prime plus higher order terms d square y d square f dy square, but I will just indicate it as a higher order terms. This is why it is called the linear stability analysis, because what I'm doing is I'm linearizing this function. Okay, so I'm neglecting all the higher order terms. Now, what is f of ys?
Steady state solution.
If I put the steady state solution into f, what should I get? 0. Because I'm finding the steady state solution by satisfying this, right? So the first term is 0 because ys satisfies that function. So what do I have left with? Just the derivative, the first derivative of the function with respect to y multiplied by y prime. That's what this is. J is called the Jacobian matrix, which is nothing but all the partial derivatives of y with respect to each one of the y. So if I have 10 equations, I will have 10 functions. I will have a 10 by 10 matrix J. Okay? That matrix is nothing but the derivative of the first function with respect to first variable, first function with respect to second variable, etc., all arranged in a row. And then I go down each row, each equation, and I construct the Jacobian. Have you done this work? Kind of? If you haven't, I will put an assignment on that so that you know how to do it. Okay, so that the stability information is contained in this matrix J. The concept that we are seeing are all applicable to the Navier-Stokes equation. It's a simple ODE, and we will make the connection from Navier-Stokes equation to ODE by simply discretizing all the spatial variables. You get maybe a million ordinary differential equations, but those equations will have a Jacobian, which will be a million times million. That depends on how many grid sizes you have. Right? But the idea is, if you give me any PDE, I can do the discretization of the spatial variables, reduce it to an ordinary differential equation. If I understand the dynamics of an ordinary differential equation, I can understand the dynamics of more complicated flow problems. Okay? So, it is this derivative that contains the information about whether it is stable or not. Is that clear? Now, if I take a simple system, one ordinary differential equation, first order ordinary differential equation. So dy dt equals lambda y. Y is my perturbed variable. Okay, in this model, this is a canonical form, and y is my perturbed variable. What does the solution to that look like? Simply e to the power lambda t. If my initial condition is y0 is equal to 1, this is my solution. Right? What are the possible behaviors of the solution that is determined by the nature of lambda? If lambda is negative and real, what happens? It just decays. That says that the perturbation y decays to 0. That means I go back to my steady state. Right? If lambda is complex, it can be complex. Right? Okay? Then it oscillates. Right? And if the real part of the complex is negative, then it oscillates but goes to 0, decays to 0, right? If the real part of lambda is positive, then it will oscillate and spiral out, blow up. If it is purely real and positive, it will just blow up. So it is the sign of the real part of this lambda that tells me whether the system is linearly stable or unstable. And I keep saying linearly because I have neglected large perturbations. I'm looking at only small perturbations because I'm looking at only this term. This term is the dominant term if the perturbation is small, because the next term will have y prime square. If y prime is small, I can neglect y prime square. So any question? So in this particular problem, ys equal to 0 is the steady state, and the steady state is stable or unstable depending on the real part of that lambda. Lambda is called eigenvalue. Okay? Now we are going to see a series of canonical examples of ordinary differential equations. Okay? So the next model is again a first order system, dx dt equals a minus x squared. So my function f of xa is simply a minus x squared. A is the parameter. As I change the parameter, I am interested in asking the question, is that system stable or not? Okay? And the initial condition is at x equal to at t equal to 0, x is equal to 0. So what do? I first find the steady state solution. So I set f of x equal to 0, and then I solve this. So that is simply x is equal to plus or minus square root of a. Right? So that is my steady state solution. The next thing is I linearize that equation. What does that linearization mean? I decompose my solution as xs, the steady state, plus the perturbation. I plug this into that equation, and I do this in a Taylor series expansion. So this is 0 because xs satisfies that function. This is my Jacobian, the derivative of that function with respect to x, evaluated at xs. So the Jacobian is evaluated at the steady state you are interested in. Now if you have multiple steady states at the same value of a, you have to test this for each steady state to see whether that steady state is stable or not. Okay? Any questions on that? So dx prime dt equals j of xs x prime. So this is my linear ordinary differential equation. But what is j in this case? It's just the derivative of f with respect to xs, and that is going to be simply minus 2xs. How do I know that? If I take the derivative of a minus x squared, a is constant. So if I take the derivative of this, it's going to give me minus 2x. But it is evaluated at the steady state, right? So I'm just writing this as minus 2xs. But in this case, that itself is the eigenvalue because I have only one ordinary differential equation. If I have two, then I have two eigenvalues. I need to solve for eigenvalue problem. Okay? So now I substitute xs equal to, I have two solutions, right? One is plus square root of a, the other one is minus square root of a. So if I put as plus square root of a, then what do I get? I put x is equal to plus square root of a.
So then it will be stable because it's negative.
It's negative, right? And a is given as a positive number. So I'm interested only in a from 0 to infinity, the parameter, right? So when xs is minus this, minus of minus will be this, plus, and it is unstable. So there are two solutions. For any given value of a, there is an upper solution and a lower solution. This is plus square root of a, this is minus square root of a. There is no solution below this value of a. For negative a, there is no solution. For positive a, there are two solutions. Okay, one is the upper one, the other one is the lower one. And what it means is if I have any initial condition starting at any point other than that on the equilibrium line, it will be attracted towards that equilibrium line. If I start from somewhere here, it will be attracted. Even if I start from here, it's not going to go to this, even though it is closer to that, right? But it will go to that because that's a stable solution. That's the attractor. The stable solution attracts any nearby trajectories. So even if you start at a point slightly below this, it's going to go away because it's a repellent, right? It's an unstable solution. So you have understood the essence of how stability analysis is done. It gets computationally complicated. Conceptually, it remains as simple as this. When you're going into study instabilities in flows, in any system, not only flow system, any dynamical system. Any questions?
I didn't really understand like why when the x has this square root of a, the
like the negative number, it will be unstable. I didn't really understand.
The first thing to ask is, do you understand that there are two solutions?
Oh yes, yeah.
Okay, they come from this, plus and minus.
Yeah.
Okay, so there is a plus square root of a as a solution, minus square root of a as a solution. Now, when I linearize this equation, I get this as my linear differential equation. The solution to that is given by e to the power lambda t.
Okay, now I
Now you get it, right? Yeah. And lambda is this. Okay. Any other questions? Okay, I think we will stop there, and in the next class we will take more complicated dynamical systems and continue the discussion with this to understand stability, transitions, etc. Okay.